Getting an overload fault or alarm can be frustrating, but once you understand what's going on, then getting it fixed is pretty straightforward. And the good news is, the free WEG programming software makes it super easy to visualize everything you need to know about overloads. I've already created a configuration and a resource, and I'm connected to the drive. Check out the WPS Quick Start video to learn how to do all of that. One of my favorite things about the WPS software is the wizards. And in particular, down here under Protections, this one that shows me exactly how the overload process works in this drive. It says if the motor current is greater than the allowed protection levels, which are defined down here, and it does it for a certain amount of time, which the drive converts to percent overload. If that overload percent rises above 6.3%, then it issues an alarm. And if it hits 100%, it issues a fault, which shuts down the drive's output. And using these three parameters, you can customize the overload curve however you want. We need to turn monitoring on for this to work, of course. When you get this darker gray background like this, you know it's active. So step 1 is to monitor the current here while running your system at full load. Whatever amperage you read, add about 10% and put that here. Now you may want to tighten or loosen that for your system, but 10% is usually a good starting point. Repeat that for the 50% speed and again for 20% speed. Again, measure the actual current under normal loads at those speeds and add about 10% and put the result in these parameters. That would give you an overload protection curve that represents your normal system loading. Looks like the default is 5 amps across the board. Now this curve is just a representative image, it doesn't change. So if we plot that ourselves, we see the default curve looks like this. Let's try this process on my motor. I'll crank it up to full speed at 60 Hertz, and we see the current is 2 amps. So I want to enter 2 amps plus about 10% here. I'll move the motor down to half speed, and it's still drawing 2 amps, so I'll put the same number here. Finally, let's take the motor down to 20% speed, which is 12 Hertz, and we see the current is 2.4 amps. So I'll put that plus 10%, or 2.6 amps, here. On our curve, that would look like this, with the green line being our actual current and the red line being the overload limit we just set. Let's do a quick check. The motor nameplate says we should be drawing about 0.9 amps at 460 volts under no load. So we would roughly double that for 230 volts, and sure enough, it's pretty close to 2 amps. Everything makes sense. Cool. It also looks like this motor draws 3.2 amps at full load, which is at the rated torque and speed. So if we add this motor's current demand to our chart, we see that the 5 amp default overload would have been way too high for this 1 horsepower motor with no load. So now if we were to add some load to my motor, and the current rose above this curve, the IXT function would take the amount the overloaded motor current exceeded the curve that we created, and it would add it to the previous amount. And it'll keep doing this over and over again as time goes on. If the motor current stays above the line, then that sum will grow, or integrate. The IXT function converts that integrated sum to a percent overload using some typical motor heating models. This curve over here shows you the result. For example, if the output current is 1.5 times the level we specified over here for the overload, a fault will occur in about 60 seconds. If the loaded current is double what we expected, then the overload will occur in about half that time. And if the actual current divided by the level we specified, or this ratio, is less than 1, then we'll never get an overload condition. Exactly what we expect. Let's try this on my motor. Now, unfortunately, I don't have a way to load this motor in my office, so I can't increase the current draw. But we can do the opposite. So instead of raising the motor current, let's just lower the overload curve to force an overload condition. The added benefit of this is I won't actually be stressing the motor with this test. It'll just look like an overload's occurred to the drive. We know this motor draws 2 amps at half speed, so let's set all the overload curve values at 0.6 amps. That means the motor current will be 3 times the overload level we set. We would expect the fault to occur in about 10 to 15 seconds. Well, let's see. I'll hit run, and look, we see the IXT integrating up. It already passed 6.3%, so we have an alarm on the drive. And when it hits 100%, bingo. We get a fault, and the drive shuts down its output in about 11 seconds. Perfect. Since the motor is no longer running, the IXT function starts to decay. We're no longer at the 100% level, so there's no longer a fault condition, and we can reset that from the keypad. But the drive thinks we massively overstressed this motor by 300%, so it uses the typical motor heating curves to slowly decay the IXT function to give the motor time to cool off. So we won't be able to reset the alarm until the IXT percent overload falls below that 6.3%, and that'll be a while. Hopefully now you can see that setting the overload curve appropriately is crucial to getting the best possible protection for your system. And that's important to understand. We just did a system overload example. That is, we measured the motor current when the system was under load and then added 10% for the overload thresholds. For us, that was a motor current of 2.2 amps, which is way below the motor's 3.2 amp ability. We weren't trying to protect the motor here, we were protecting the system. If we just wanted to protect the motor, then we would simply look at the full load amps on the nameplate, add a little, 10% is usually pretty good, and use that for these overload threshold numbers. Now we would be protecting the motor from burning itself out. Exact same process, just a different point of view. A couple side notes. First, you can send this IXT signal to an analog output, so you can watch it in real time on a scope. This WPS software is great, but it does take time to update the screen, so you don't actually see everything that happens. When you watch it on the scope, you get a much better feel for exactly what's happening and when. Second, when using these wizards, remember that you can save the exact setup you have simply by closing it and saying, yes, I would like to save this. That's this guy over here, so select it or double click on it to open it. And you can rename it if you want to. Finally, you can print all the values in this wizard if you need to document what you've done. Well, that ought to be enough to get you going with overloads. Click here to learn more about the WEG CFW300 variable frequency drive. Click here to learn about Automation Direct's free award-winning support options, and click here to subscribe to our YouTube channel so you'll be notified when we publish new videos.